Okay, and so where we left off was right here on this slide, was discussing categories of electrons. And there are three categories of electrons that you have to be aware of: inner, or what we sometimes call core electrons, outer electrons, and valence electrons. So you have to be aware of all three of these definitions. They're not meant to be anything, majorly complicated. They're just more definitions that you need to be aware of. So the first one is the inner or core electrons are those that an atom has in common with the previous noble gas and any completed transition series. So if you look at the noble gas that precedes the element whose electron configuration you're looking at, so say for example phosphorus, right? If we look at phosphorus, well, the noble gas that precedes phosphorus is neon, and neon is element number 10, so that means that phosphorus has a total of 10 inner or core electrons. If we look at manganese, the noble gas that precedes manganese is argon, and argon is element number 18, and so manganese has a total of 18 inner electrons. Now remember, when we involve electrons from a transition series, they have to be completed. So that means you'd have to have a full set of d electrons. And since you can have a total of 10 d electrons, and there's only 5 d electrons in manganese, we don't consider those d electrons. What else? If you look at tellurium, here's an example where we do have a completed d series. And so if you look at the noble gas krypton, which precedes tellurium, krypton has a total of 36 electrons, but we have to add on, we have to tack on these 10 electrons, because that is a completed transition series right there. Okay, so those are inner or core electrons. The only thing here that gives students some trouble sometimes is memorizing that you have to include the d electrons when they're completed. So just be aware of that. The next one is the outer electrons. So I think this is the easiest one. Outer electrons are just any electrons with the highest n value. So whatever has the highest principal quantum number value, those are the outer electrons. So if you look at phosphorus, you see we have 3 as the highest principal quantum number. Well, all of those are going to be considered outer electrons. So since we have 3s2 and 3p3, 2 plus 3 is 5, we have a total of 5 outer electrons. Manganese, again, the highest principal quantum number is 4. Those are the only ones we consider. So we have 2 outer electrons. And with tellurium, we have the principal quantum number 5 showing up twice in these two sublevels, 5s and 5p. And then we have a total of 2 here and 4 here. So we add them up and we get a total of 6 outer electrons. Now, with valence electrons, it's kind of interesting because you have to consider there's 2 different definitions. There's valence electrons for main group elements, that's the A group elements, and then for transition metals or transition elements, there's a little different, there's a sort of a nuance here to the rule. It says valence electrons are those involved in forming compounds, and so valence electrons are really important in this class because as we start to understand reactivity of atoms and molecules and ions more and more, we have to take a look at the valence electrons in order to understand reactivity. Anyhow, for main group elements, so that's the A group, the valence electrons are just the outer electrons. So that's pretty simple, okay? So if I look at phosphorus or tellurium, those are both main group elements, okay? And so I look at the highest principal quantum number, I get a total of 5 here. I look at the highest principal quantum number in tellurium, I get a total of 6 here. Now manganese is a transition metal. The valence electrons for transition metals are not only those with the highest n, the outer electrons, okay? So remember, outer electrons are highest n, okay? But you also consider the n-1 d electron. So if we look at manganese, the highest principal quantum number is 4, and then the n-1 d electrons would be the 3 d electrons. So we tally all those up and we get a total of 7 valence electrons. I know it's early, I know it's 9:30, but give me a thumbs up if you just follow me on that. You're like, oh, Mr. Dean, I'm just going to have to look at the definitions a few times and then I'm going to have it down pat. You can count on me. I'm going to know what that means. Thanks, Amanda. All right. So Amanda's good to go. Liv, who else? Aurora, the whole gang. Good. Okay, well, let's move on from there and take a look at a problem. Yeah. Okay. So it says here, Using only the periodic table, your best friend in this chapter, and assuming a regular filling pattern. When it says assuming a regular filling pattern, that just means it follows the Aufbau principle, Hund's rule. Give the full and condensed electron configurations, partial orbital diagram showing valence electrons only, and the number of inner electrons. Well, I don't know if we have time to do all these, but let's tackle the first one. Let's give potassium the old college try here. So potassium has a total of 19 electrons. I'm not going to project my periodic table because remember, you should always come to this lecture with a periodic table. I recommend, instead of using a beautiful laminated one that you bought from some kind of, maybe from Jeff Bezos or the bookstore or something, I would recommend just printing out a few of them on just regular printer paper so that you can write all over them, right? You can scribble all over it. Anyhow, so for potassium, we have a total of 19 electrons. So we have 1s2, 2s2. After that, we have 2p. We have 6. So far, we've covered 10 electrons. Then we go to 3s2, 3p, 6. And since potassium is in group 1a, it has a 4s1 electron. And if you add all that up, you have 10 plus 8 is 18 plus 1 is 19. Good. There we go. So that's all the electrons in potassium. This is the full electron configuration. So I should have written here full electron configuration. If we want to write the condensed, so condensed, all right, what do we do with the condensed? We're going to take all of the core electrons, okay? So these are core or inner electrons because we look at the noble gas that precedes it, okay? And the noble gas that precedes potassium is argon. And so the condensed electron configuration, we put argon, which covers all of those first 10 electrons. Let me fix that. Mr. Dion needs to wake up a little bit more. Okay, there we go. All right, goes all the way up to argon. Whew, argon has 18 electrons. I don't know what I was thinking there. Anyhow, so we have argon, and then we have 4s1 like that. That's our condensed. Now, next it says to give the what? Partial orbital diagram showing valence electrons only. Well, if we do the orbital diagram, I mean, there's probably a few ways that you could do this, but I think probably the easiest way is like this. We have the 4s orbital. There's only one type of 4s orbital. After 4s, we have the 3d. Now, obviously, we have no electrons in the 3d, but we're going to write out all the orbitals for that period. And then we have the 4p, which has 3, so 4p. And there's only one stinking electron, so I would just put in that electron like that and call it a day, okay? Nothing more than that. Let's try the next one, which is technetium. Technetium has a total of 43 electrons. Let's get to it. Do it and add it into it. So if we want to get the full electron configuration, let's go. We have 1s2, 2s2. Okay, that's 4. We got 39 plus 2. And 2p6. Okay, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. In technetium, element number 43. So at 4s2, I'm at strontium. Then I have yttrium, zirconium, niobium, molybdenum, technetium. That means I've got a total of 4d5, like that. Okay, there we go. So that's the full electron configuration. Let's get on the condensed bandwagon here. Okay, so the noble gas that precedes technetium. Who could tell me what it is? Does anybody know? Matthew, do you know? What's the noble gas that precedes technetium? Not meant to be a mind-boggling question. Just, yeah, that's right. It's krypton. Absolutely. Good. So we want to do the condensed. Okay, condensed. Here we go. Thanks, Matthew. Good. So we have krypton. So we're going to go all the way up to here. Right? That covers krypton. So we have krypton in our square brackets. We have 5s2, 4d5, like that. Okay. Same thing with the partial orbital diagram. We draw out all the orbitals in that period. So we'll write out for tellurium. We have 5s orbital. Then after that, we have 4d. There's 5 types of d orbital, so 4d. And then we have a 5p, 1, 2, 3, like that. Okay, so let's we're gonna fill in these guys right here. So we have 5s1, 2, 1, 2, 3, 4, 5. There you go. All right. Hey, can I ask you guys a question? And this is me just kind of spot checking to see, did anybody complete the Learn Smart? Do you think technetium, would it be attracted to a magnetic field? Yes or no? Does anybody have an inkling after reading the textbook? And we'll cover it at the end of the lecture, but I'm just interested if anybody caught that. Would technetium be attracted to a magnetic field? Yay or nay? If somebody, Kenner says, yes, I think. Amanda says yes. Yeah, I think the yeses have it. Okay, and what you're going to see at the end of the lecture is that when you have unpaired electrons, like all of these electrons are unpaired. Unpaired electrons. When an atom has unpaired electrons, it's going to be attracted to a magnetic field. Okay, and we call that being paramagnetic. And don't worry, I'll cover it at the end of the lecture. I just wanted to see. I know that some of you like to read ahead. Anyhow, somebody says, why did you put the 5p if it's still left blank? Because when you put in the partial orbital diagram, you include all the orbitals in that period. Okay, you write out all the orbitals in that period. You don't have to. Okay, if you look at the solutions, I don't think that they do. Yeah, they do here for this one, and they do for this one too. Yeah, so it depends on the book, I suppose. But I always like to write out every orbital for that period. Anyhow, let's move ahead and let's talk about trends in atomic size. It says here that, and again, this is something that we talked about in chapter 14 in some detail. We said that atomic size increases as the principal quantum number increases. So what does that mean? If you go down a group or a family, like say the alkali metals, as you go from hydrogen to lithium to sodium, you go from a principal quantum number of n is equal to 1, to n is equal to 2, to n is equal to 3, so on and so forth. And as that n increases, what does that mean? That means the size of the orbital is going to get bigger and bigger and bigger. As the n increases, the probability that the outer electrons will be further from the nucleus increases. And so as we go down a group, the atomic size is going to get bigger and bigger. Now, this is something I spent quite a bit of time on that fateful day when we discussed chapter 14, was the fact that atomic size decreases across a period. And the reason why, it was based on what? ZF, which is effective nuclear charge, right? This is something I really like to explain in the face-to-face classroom because I can actually wave my hands at the periodic table in front of you. But the idea is this: as we go across the period, the number of protons keeps increasing. And as that nuclear charge increases, the number of shielding electrons or inner or core electrons doesn't increase. It stays the same. And so the electrons that are outer electrons start to feel more and more and more of that positive charge. And so they rein in those outer electrons, the atom reins in those outer electrons as more of the effective nuclear charge is experienced. Okay. Summarized here, probably even more eloquently, it says, as the effective nuclear charge increases, outer electrons are simply pulled closer to the nucleus, okay, rendering atomics or atoms smaller as we go across a period. Now it says here, for main group elements, the atomic size increases down a group in the periodic table and decreases across a period. This is basically a one-sentence summary of this entire slide. And that's all you need to know, okay? I'll be honest with you guys. The book, she goes into quite a few exceptions to this rule, okay? Goes into quite a few exceptions. You don't have to know the exceptions about atomic size. You just need to know the general ideas that I just put forth, that when you go across a period, you can see that the atomic size, generally speaking, does decrease. And when you go down a group like this, right, we have higher n, bigger size, okay? And in the book, she goes into quite a bit of detail about the transition metals and why they don't vary in size a whole lot. You can see there's very little variation here. I can tell you very quickly that the reason why is because as you go across here, right, you're increasing the number of protons, but since you're adding d electrons, those are inner electrons, okay? And so every time you add a proton, it's going to affect the shielding, you know, such that the atomic size is going to remain the same. All right. Anyhow, with that in mind, this is the kind of problem that I will ask on the next midterm. It says here, using only the periodic table and your widths, okay, rank each set of main group elements in order of decreasing atomic size. So we want to go from large to small, okay? So let's do that. Okay, so we want to go from large, let's set it up like this. Come on, go from large to small, like that. Well, if we look at calcium, magnesium, and strontium, okay, can anybody tell me what those elements all have in common? Calcium, strontium, and magnesium? Yeah, exactly. Somebody says they're alkaline earths. Yeah, they're all group 2 elements. So all group 2A elements. Okay, and what's the trend here? Is that as the principal quantum number increases, the elements are going to get bigger and bigger and bigger. And so strontium is found in period 5. And so it's going to be the largest one. So we have strontium. The smallest one is going to be magnesium because it's found in period 3. So we'll put magnesium down here, and calcium is in between. Calcium is in period 4. Let's take a look at the next example. Okay, we have potassium, gallium, and calcium. Can anybody tell me what these ones have in common? What do these guys all have in common? Not a trick question. Yeah, exactly. My students are saying that these are all in the same period. Yes, they're all in the 4th period. So all in 4th period. And what was the trend? That as we go across a period, the atomic size is going to decrease. So that means whichever one has the highest atomic number is going to be the smallest one. And the one with the highest atomic number is gallium. Okay, so it's the smallest. The one with the lowest atomic number is potassium. And then calcium comes right after potassium. So we got it set up like that. Okay, the next one's more of an, kind of a plethora here. But the way I would solve this one is you've got bromine. So bromine is a halogen in the 4th period. Then you've got rubidium. You've got rubidium and potassium. Rubidium and krypton, jeepers. Anyhow, bromine and krypton. So bromine and krypton are both in the same period, okay? And rubidium is in the lower period, okay? So we'll put here bromine and krypton are both in period 4, so period 4, and then rubidium is in period 5. So we'll put that down here. So period 5. And rubidium is also far on the left-hand side of the periodic table. So it's going to be by far the biggest. So we'll put rubidium first, okay? By far it's going to be the largest. Then if we compare bromine and krypton, which both have a lower principal quantum number than rubidium, which one of those is going to be smaller? Well, it's going to be the noble gas because it's further to the right side. It feels more of the effective nuclear charge. And so krypton is going to be the smallest one. And then we'll put the bromine in the middle like that. In the interest of time, I'm going to just kind of move on from the last one, and I'll help you out with it. It goes rubidium, strontium, and calcium, and I'll let you try to figure that one out on your own. But let's move forward, and of course, the solutions are shown here. This shows you the trend of periodicity the periodicity of the atomic radius. What does periodicity mean? It means repeating, right? A repetitive or a pattern that you see in the periodic table. For example, if you look at the alkali metals, right? If you look at the alkali metals, they feel very little effective nuclear charge, right? Because they have one other electron, okay? And so those are all at the top, right? And if you look at the noble gases, those are all at the bottom. Now, this is just a graphical representation of atomic radius, and you can see that generally speaking, as we go across a period, so let's say we choose period 2, okay, as we go from lithium to neon, you can see that the atomic size decreases. right? In period 3, you can see it decreases. Once we get to the 4th period where we have the transition metals, you see we have some anomalies in here. I'm not going to ask you about those, okay? It's not my job to try to ask you about every single exception that comes up. Some exceptions for sure, okay? But when there's an exception that I really want you to know, I will highlight that exception for you, okay? And so you need to know that generally speaking, as we go across a period, atomic size decreases, and as we go down a group, atomic size increases. All right, ionization energy is also something that we spoke about in chapter 14, so I'll go over this a little bit quickly. You might remember that when we discussed this, if we looked at the periodic table, and I'll just draw a generic shape, the rectangular shape of the periodic table, the ionization energy increases in this direction going across a period, and it increases going up a group like this. So ionization energy. It says here that ionization energy is the energy that's required for the complete removal of 1 mole of electrons from 1 mole of gaseous atoms or ions. So if you're ripping electrons off, that's ionization energy. So atoms with a low ionization energy, that means it takes very little energy to remove an electron. Well, what does that mean? That tells you that the atom is happy to lose an electron, right? If the atom isn't holding on to the electron very tightly, it's like, meh, take it, take it, and I'll become what? A cation. Conversely, if an atom has a high ionization energy, right, it's like hanging on to its electrons like grim death, that means that it's going to want to form an anion normally. Okay, exceptions to that would be the noble gases, who are completely content the way they are. But ionization energy again tends to decrease down a group and increase across a period. All right, here's a graphical representation of ionization energy. And again, I'm not going to ask you about the anomalies that you see here. There's some blips. They are covered in the textbook. If you want to go over those and write yourself a 10-page essay for your own personal edification, feel free to do that. Okay, it's not even meant to be anything really complicated, okay, these anomalies. In fact, maybe I could show it to you later on if we have time. But in the interest of time, what you need to know is that generally speaking, as we go across a period, ionization energy increases, right? What else do you need to know? You need to know that the ionization energy of the noble gases is going to be really high, and the ionization energy of the alkali metals will be the lowest, right? They don't mind losing an electron. In fact, you see that alkali metals and alkaline earth tend to lose electrons quite easily, okay? I should say comparatively, compared to other elements, okay? Here's sort of a bar graph of ionization energies, and you can see that the ionization energies of the alkali metals is really low. Then we go to the alkaline earths, it increases, it increases, 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 okay? So again, if you're kind of like, I see the trend, Mr. Dion, but what does it mean? Okay, I'll explain it to you again. If the ionization energy of these elements here, where's my pen? If the ionization energy of these alkali metals, for example, is really low, what is the definition of ionization energy? It's the amount of energy required to remove an electron from 1 mole of atoms in the gaseous state. So that means it takes 520 kilojoules per mole to remove 1 mole of electrons from 1 mole of lithium. But if you go to beryllium, it takes more energy. Why would that be? It's because the effective nuclear charge increased, right? If the outer electrons are feeling more of that nuclear charge, they're going to be held more tightly. Therefore, it's going to take more energy to rip an electron off. Okay? That's the rationale. Okay? Look at fluorine. It's got a much higher ionization energy. Why? Because the effective nuclear charge is even higher. Okay, in our book, let me just kind of mention this to you as sort of a comment, is that I hope you're all reading the book. There's one comment that she makes in there. She says, all atomic trends can be explained using electron configuration and effective nuclear charge. So effective nuclear charge is a really powerful concept that can really get you out of a jam, okay? If you understand that concept, it can take you a lot of places in chemistry class. Okay, that's enough about that. It says here, rank the elements in each set in order of decreasing ionization energy. So we'll go over here. So we'll go from highest to lowest. So highest highest ionization energy. And then we'll go down here to lowest ionization energy. We'll start with the first one. We got krypton, helium, and argon. So krypton, helium, and argon. What do these elements all have in common? And I know you know the answer, but I'll just double check. And it's nice to know that somebody's out there listening. What do these guys all have in common? They're all what? Yeah, thanks, Aurora. They're all noble gases, right? So these are all noble gases. So that means they're all in the same group. And what was the rule? We said the ionization energy decreases going down a group. So the one with the lowest ionization energy will be the noble gas with the highest principal quantum number, which would be krypton. And then helium will have the highest ionization energy. And argon will be somewhere in between. The next one has antimony, tellurium, and tin. Those are all kind of gathered together there down in the fifth period in the P block, tin, antimony, and tellurium. And so I'll put here, these are all period. Maybe I'll use a different coloring. These are all period 5. Okay, they're all in period 5. And what was the trend? We said that as we go from left to right across the periodic table, the ionization energy increases. Okay, and so the one with the highest ionization energy is going to be tellurium, because it has the lowest atomic number. Then next we have antimony, and then the biggest one of all of these is going to be tin, so it's going to have the lowest ionization energy. Tin, snuff, right? Anyhow, in the interest of time, we'll move past the next two. The solutions are found here, and let's take a look at this one right here. This is the ionization energy of beryllium. So let me show you something really cool. You guys ready for something that's really fun? Okay, and I'm not kidding. When I say fun, I mean it. Capital F. Okay, so beryllium. What's the electron configuration? Electron configuration of beryllium: 1s2, 2s2. Okay, so it's got these as the core or inner electrons. So these are core electrons, right? And these are valence electrons. You guys want to see something neat? Okay, so this is in megajoules per mole, the units here. I don't know why she changes that up. I don't know why she just doesn't stick to kilojoules per mole. I don't know. Anyway, if you rip off an electron off of beryllium, right? Okay, so if you make beryllium plus, yeah, let me use a different color. If you make a Be plus cation, right, you've got 1s2, 2s1. Well, that's the first ionization energy, right? That's ionization energy 1. And it takes 0.9 megajoules per mole, okay? I kind of got to go on an angle here, you guys. Anyhow, if you rip off another electron, that's going to be ionization energy 2. What does that mean? That means you're removing another electron, okay? So that means you're going to end up with Be 2 plus, and then your electron configuration is going to be 1s2, okay? The amount of energy is 1.76, megajoules per mole. Okay, cool. If you remove another electron, okay, so if you take another one off, so you get ionization energy 3, you'd end up with beryllium 3 plus, like that, and then you'd have 1s1. Now, what you're doing here, though, is that you see that the ionization energy skyrockets, right? It jumps by a huge amount. Why? Because you're removing what? You're removing a core electron, right? You removed a 1s electron. Those are core electrons. Core electrons, holy smokes, man. Those are going to be held a lot tighter, right? They're core. They're on the inside, okay? They don't like to leave, okay? Give me a thumbs up if you follow me on that concept. I always think this is a fun concept. Yeah, thanks, Joel. And you know what makes this so cool? Okay, what makes this so fun for students is that I don't think it's a mind-boggling concept. Okay, I'm not going to use the word simple because I don't think simple is a word that should be used in chemistry class a whole heck of a lot. Okay, but why this is so neat is that you can actually look at a table of ionization energies and predict the number of valence electrons in an atom. Let me give you an example. Let me just pick any atom here at random, okay? Let's pick, I don't know, let's pick oxygen, okay? So we'll pick oxygen. And if we write out the electron configuration of oxygen, oxygen is 1s2, 2s2, and then we have 2p4. So that means it has how many valence electrons? It's got 1, 2, 3, 4, 5, 6. These are valence electrons. Okay, and then it's got 2 core electrons. Okay, let's look at the ionization energy. So you have the first one, then you go to the next one. It's about double plus a bit, you know, maybe 2.5 times, and it jumps up again, 7.47. Again, this is in megajoules per mole, 10.98, 13. But then looky here, you do this giant leap, right? All the rest of them were kind of normal, and then you did this humongous jump from 13.33 to 71.3. That tells you that you had a total of 1, 2, 3, 4, 5, 6 valence electrons. So what I'm getting at, you guys, is that I could give you values of ionization energy, and you could just identify the number of valence electrons, boom, just by looking at the numbers. And you're like, do I have to memorize these numbers? No, you just look for the big change. Let me show you an example. It says here, name the mystery element. It's a period 3 element with the following ionization energies, and write its full electron configuration. Let's forget about the periodic table right now, and let's just look at the ionization energies closely. Can anybody tell me where the big jump is here? Maybe I'll just ask my students. They know a lot of stuff. Where do you guys see the big jump? Going from where to where? Yeah, exactly. You all nailed it. Exactly. Nobody has the wrong answer, okay? That's a nice way of saying everybody has the right answer, okay? So look, we go from 1012 to 1903. They seem to go up by about 1,000 here. Then it's roughly, 2,000 there. Then you get, more here, 1,500 roughly. And then you get this huge jump going from 5 to 6, right? Sorry. I'm not talking to you, Siri. You're not paying tuition. Anyhow, you go from ionization energy 5 to ionization energy 6. You have this huge leap. Okay, so that tells you that this period 3 element has 5 valence electrons. Now, somebody tell me what the element is. Who's got an idea? What period 3 element has 5 valence electrons? Nitrogen is a period 2 element. So period 3 starts with sodium. Yeah, it's phosphorus. Right, so period 3, right, what are the elements in period 3? Period 3 has sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Look, we have 1, 2, 3, 4, 5. Oops, I should have used something better than that. 5, so it must be phosphorus. All right, phosphorus has 5 valence electrons. Don't believe me? Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. There are the valence electrons and valence, and there are a total of 1, 2, 3, 4, 5 of them. There we go, 5 valence electrons. Okay, cool, huh? Give me a thumbs up if you think you could nail that. Like Mr. Dion, I could do that question in my sleep. Just try me. Good, because if you got it correct, I'd be just as happy as you. All right. Okay. Element was phosphorus. Let's talk about electron affinity. Electron affinity is one of those ones. Yeah, I even say it right here. The trends in electron affinity are not as abundantly clear as they are in atomic size and ionization energy. All you need to know is the general trend of electron affinity. It says here that electron affinity is the energy change that occurs when 1 mole of electrons is added, right? If you have an affinity for something, it means you like it, you want it, okay? So as 1 mole of electrons is added to 1 mole of gaseous atoms or ions, it says atoms with a low electron affinity tend to form cations. These are metals. Metals like to form cations. And atoms with high electron affinity tend to form anions, and these are nonmetals. nonmetals. Okay, the trends for electron affinity, again, are not nearly as regular as those is ionization energy. Okay, now electron affinity generally increases across a period as nuclear charge increases, and generally decreases down a group as the nucleus gets farther and farther away from the outside. But this, that trend really only holds true for group 1A. And so you just have to know the general rule, which I have in a couple of slides coming up. And in fact, I'll show you, I'll skip these two slides here, and I'll show you that electron affinity. You even see that she uses dashed lines because she says there's many, many, many exceptions to this, okay? So if we back up, again, I'm going to show you the many exceptions. You just need to know the general trend, okay? Again, you can see generally it increases, but, there's all kinds of flip-flopping here, so I'm not going to spend a ton of time on that. It's one of those things I could talk about all day. But there is some information, some very important information to be gained here, okay? Behavior patterns for ionization energy and electron affinity. Okay, let's stop for a second, take a deep breath, and really think about this. Okay, we're taking a break. Okay, break's over. It says here, reactive nonmetals. Okay, so what's a nonmetal? That's something on the right-hand 1/3 of the periodic table, the right side of the metalloid line. Reactive nonmetals have high ionization energies, so that means they don't like to lose electrons, and highly negative electron affinities. If the electron affinity is negative, that means the energy is being released, and that's going to be a favorable process, right? It's going to lose energy in the process, right? It's going to become more stable, okay? It says these elements attract electrons strongly and tend to form negative ions, okay? An example would be something like chlorine, right? Chlorine usually exists as chloride. What about fluorine? That usually exists as fluoride, okay? Now, reactive metals have low ionization energies. That means it's easier to remove electrons from them and slightly negative electron affinities, right? They don't want to gain electrons as much as nonmetals. And so these elements tend to lose electrons easily and form cations, okay? Now, the noble gases have very high ionization energies and slightly positive electron affinities. The bottom line for noble gases is that they don't want to gain or lose electrons, okay? So again, some examples of reactive nonmetals. These would be things like iodine, chlorine, bromine, sulfur, oxygen, fluorine, right? If we're talking about reactive metals, we're talking about things like sodium, potassium, lithium, calcium, magnesium, things like that. Okay. Here's a slide that I already showed you in chapter 14. So I'm going to move on from there and talk a little bit more about metals and metallic behavior. Okay, so this says here that metals are typically shiny solids with moderate to high melting points. There are exceptions to this, right? Gallium is a metal that's not very hard. It can, it can be melted in your hand. Mercury is a liquid. So there are exceptions to this, but generally speaking, they're shiny solids with moderate to high melting points. Good conductors of heat and electricity can be easily shaped. So malleable means it's something that can be pounded into a sheet, and ductile means that a metal can be formed into a wire, so drawn out into a wire. Metals tend to lose electrons and form cations, okay? And we say that they're easily oxidized. All right, have you guys ever heard the acronym? Did I teach you guys the acronym oil rig in this class? I can't remember. I've got so many classes on the go right now. Have I gone over oil rig? Somebody says, not yet. Okay, Brittany, thank you. Okay. Somebody says, doesn't ring a bell. Well, let me start ringing it for you. Okay. So oil, what that stands for is oxidation is losing electrons. Okay. So if an element loses electrons, we say that it's being oxidized, losing electrons. Okay. It says here that metals are generally strong reducing agents. And for that, we say rig, so oil rig. And rig stands for reduction is gaining. Gaining electrons. There we go. Okay. Most metals form ionic oxides, which are basic in aqueous solution In nonmetals, some nonmetals tend to form acidic solutions with their oxides. Anyhow, so metallic behavior, generally speaking, as we move across the periodic table from left to right, it tends to decrease, right? Because the effective nuclear charge increases, and atoms don't want to give up electrons. Metallic behavior increases down a group because its principal quantum number increases. The outer electrons are further and further from the nucleus. All right, let's talk a little bit more about oxidation and talk about what oxidation numbers are. Okay. Let me see here. What slide is this? You know what? I'm going to take a chance here, and I'm going to go way back to this. No, I don't know. You know what? Let's just do it. I'll just use this. Okay. Sorry, you guys. I'm going to have to back up here a little bit because I want to show you something. I'll erase some of this stuff so it doesn't throw you off. Okay. And the only reason I'm using this is because I don't have a prettier periodic table to use. I just want to go over this quickly with you, okay? Rig is reduction is gaining. All right, so if we have here, let's pick a let's pick a metal like sodium. So sodium is found right here. Sodium is found here in the periodic table. There's sodium. The reason sodium will lose an electron and form sodium plus, right? The reason you end up with a metal losing an electron is because the sodium has an identity crisis, okay? An element will always gain or lose electrons so that it will have the same number of electrons as the nearest noble gas. What's the nearest noble gas? Not the noble gas that precedes it or follows it. That wasn't what I said. I said the closest noble gas to sodium. Did anybody tell me? Not a trick question. Yeah, Aurora says it's neon. She's absolutely right. Yeah, Joel says the same thing. So neon is the closest noble gas to sodium. Well, sodium has 11 electrons, but neon has 10 electrons. So that means that sodium will lose 1 electron so that it has the same number of electrons as neon. Now, the same number of electrons, instead of me keeping, saying that over and over and over, there's a nicer word for it, and it's isoelectronic. So you would say that sodium cation, the Na+, is isoelectronic with neon. That means it's got 10 electrons, it's got the same number of electrons as neon. Cool? Okay, let's pick another example. What if I chose calcium? Calcium is found right here. I'll write in Ca. What's the closest noble gas to calcium? Not a trick question. Closest. Who's closest? Yeah, you're all right. Okay, every single one of you is right. You put an answer. And the answer is this one right here. It's argon. Okay, now calcium has a total of 20 electrons, but argon has 18 electrons. But if calcium loses 2 electrons to become Ca2+, it becomes isoelectronic with the noble gas argon. We can do the exact same thing for nonmetals. So let me scribble, remove some of this scribble that I have here, okay? Let's pick a nonmetal. I don't know. Let's choose phosphorus, okay? So phosphorus is found right here, 1, 2, 3. Phosphorus is found right here. Now here we go. I'm going to ask you guys, what's the closest noble gas to phosphorus? Closest. Anybody nail that? Somebody says, I'll wait until another person answers because I can't tell if that's a new or an old answer. Good. Yeah, it's argon. Yeah, thank you. It's argon. Argon is actually the closest noble gas. Now, argon has a total of 18 electrons. Phosphorus has a total of 15 electrons, right? So how many electrons does phosphorus have to gain to become isoelectronic with argon? 1, 2, 3. And that's why phosphorus is usually P3-. This isn't, magic. Okay, that's the reason why oxygen, right? Here's where oxygen is found, right here. Oxygen has to gain 1, 2 electrons to become isoelectronic with neon, and that's why oxygen is O2-. Okay, nothing more than that. Let's try one more, and then we'll move on. What if I had this one, aluminum? should aluminum gain or lose electrons to become isoelectronic with a noble gas? This one's maybe a little trickier. I'm waiting for an answer here. What would aluminum do? It has to lose electrons, right? Aluminum is going to lose electrons because the closest noble gas to aluminum is neon. Okay, it's not argon. Neon is in fact closer. Let me prove it to you. In order for aluminum to become isoelectronic with neon, it has to lose, watch, 1, 2, 3. There we go. That's why aluminum forms aluminum 3+. If it became isoelectronic with argon, it would have to gain 1, 2, 3, 4, 5. Not going to do it. Okay. All right. I sound like George Bush Sr. Anyhow, not going to happen. Okay. All right. Give me a thumbs up if you follow me on that. While you're answered me, I'll try to figure out where the heck I was in the slides. Does anybody follow me on that? All right, great. What do you think? Is that kind of a cool concept or what? Becoming isoelectronic with a noble gas. Yeah, anyhow. Here's the oxidation numbers, highest and lowest, if applicable, for reactive main group elements. Okay, you can see that the metals are more limited in the number of oxidation states for main group elements, but the non-metals can take on various oxidation states. Anyhow, my general rule still stands though, that oxygen will gain 2 electrons, nitrogen will gain 3 electrons. Carbon is tricky, it can have a whole plethora of oxidation states. Anywho, the whole thing about oxide behavior, I can't even imagine what I would ask you about this except really what is just summarized on the next 2 slides. I can't imagine going beyond that. But it says here that if you have an oxide, so CaO is calcium oxide, right? You should know how to name that. The one below it is tetraphosphorus decoxide. You should know how to name that. Now, calcium is a metal, right? So since this is the oxide of a main group metal, if you put that in water, okay, it's going to be basic. Okay, it makes a basic solution. Okay, if you take the oxide of a non-metal and you put it in solution, it makes an acidic solution. Now, if you're wondering why these are different colors, it's because there's indicators in here to show whether these are acidic or basic solutions. But really, there's nothing more than that because I feel like the book, she goes into some specific examples, but not a ton of general rules. Let's go over this slide quickly, and then we'll move on to electron configurations of ions. But it says here that main group metals form ionic oxides, which are basic in aqueous solution. Main group nonmetals form covalent oxides, which are acidic. But some metals and metalloids form amphoteric oxides, which can act as both acids or bases in water. So it depends on the situation. But if you have aluminum oxide, this is aluminum oxide here. If you treat that with an acid, it behaves like a base, okay? If you treat it with a base, it behaves as an acid. So it depends on the situation. All right, well, let's move on from that and talk about electron configuration again. And now we're going to look at the electron configuration of ions. All right, so it says here the elements at either end of a period gain or lose electrons to attain a filled outer level, right? That's just a politically correct way of saying atoms will do whatever they can to become isoelectronic with a noble gas, right? So I went over sodium, why it loses an electron, because then it becomes isoelectronic with the nearest noble gas, which is neon. Bromine is a halogen. The halogens tend to gain electrons or gain 1 electron to become isoelectronic with a noble gas. Now, if you look at bromine in the periodic table, it's element number 35. The nearest noble gas is right next door. It's krypton, which is element number 36. And so bromine will have to gain 1 electron. And that's why bromine tends to form bromide. And again, that's why sodium tends to form a sodium cation like that. Here's a little, figure that comes from our book. So basically, she's just trying to help you out in that you know that you start with the noble gases here. Oxygen would have to gain 1, 2. So that's why everything here is going to have a 2 minus charge. The halogens have to gain 1, and so that's why the halogens have a 1 minus charge. The alkali metals have to lose 1 electron, and that's why they have a +1 charge, and that's why these guys have a +2 charge. Okay? Anyhow, there you go. All right. There you go. Okay, let's move on from there. So electron configurations of monatomic ions. It says here that a pseudo-noble gas configuration is attained when a metal atom empties its highest energy level. So pseudo-noble gas configuration. It says here that the ion attains the stability of the empty NS and NP sublevels in a filled N-1 D sublevel. So when we have a metal and it has d electrons, okay, it's going to empty out just the ones with the highest principal quantum number. So these ones and these ones. That's why tin can form the tin 4+ ion, right? Because it loses all 4 of these 5s and 5p electrons, and we end up with krypton, right? Those are our core electrons, plus we end up with the d electrons, and we call that a pseudo-noble gas configuration. But it also says here that a noble gas or a metal may lose only the p electrons to attain what's called an inert pair configuration. And that's why tin can also be tin 2+, because if you lose just the p electrons, you still have the 2s electrons, and we call that an inert pair configuration. All right. With that in mind, let's try a problem. It says here, using condensed electron configurations, write equations representing the formation of the ions of the following elements. Look, I'm not big on this whole writing equations of forming ions. I'll go over it with you. What I want you to understand is electron configurations of ions. So with that in mind, let's take a look at iodine. Give myself some more room down here. Okay, so we'll start with iodine. And so if we take iodine, can anybody tell me, would iodine like to gain or lose electrons, and how many electrons? Could anybody identify that for me? Yeah, iodine likes to gain 1 electron so that it can become isoelectronic with xenon. And we could write that out, that iodine plus an electron gives you I-, like that. So then we could write out the complete electron configuration for iodine. So iodine is, the core electrons of iodine is krypton. And then after krypton, what do we have? We have 5s2, 4d10. So 5s2, 4d10. Then we have 5p6. And then we're going to add the electron to it, and we're going to end up with I-. What's the electron configuration of I-? All we have to do is take this electron and add it. Did I put 4p6 when I should have put 4p5? Oh, Mr. Dion. There we go. 5p5. All we have to do is add that electron to the 5p orbital, like that, and we end up with krypton, 5s2, 4d10, 5p6. And you can see that all of the outer levels are all completely filled, right? Isoelectronic with a noble gas. Let's give the next one the old college try. It's potassium. I'll make some room here for potassium. So if we take potassium, who could tell me, would potassium want to gain or lose electrons? And if so, how many? Yeah, Aaron says lose 1. I agree. Yes, so potassium is going to become K plus an electron, because then it will be isoelectronic with argon, which is 18 electrons. And so let's write out the electron configuration of potassium, which is argon, and then 4s2, and then it's going to become Did I put 4s2 when it's 4s1? Jeepers. Oh, I think I'm tired. Is anybody else tired? Just me? Okay, so then we end up with K plus is being argon plus the electron like that. Okay, Violet's tired. Okay, one of us is tired. Okay, Alexis says, would you have us do ions with any of the weird ones? I'm trying to think if I've ever asked a question with a transition metal. Yeah, I could. That would be reasonable. I mean, the main thing is that either way, you have to understand those exceptions, right? You have to know the exceptions in the periodic table. Let's try. No, let's move on. Let's keep going. What time is it? 10:22. I want to finish out this chapter, and the last section deals with. No, not the last section. We have a couple sections. We have paramagnetism, and then oh yeah, I want to talk about the size of ions. You're gonna love that part. Okay. Let's talk about paramagnetism and diamagnetism kind of quickly. I already mentioned this to you earlier today in the slide because it's kind of a fun thing. And I know that I say that about everything. I always say, this is fun, that is fun. And you're like, I resent that. You know, it's a chemistry class. But anyhow, I think it's fun. Anyhow, it says here that a species with one or more unpaired electrons exhibits what's called paramagnetism. All you need to know, you guys, is that if you have unpaired electrons in your electron configuration, when you evaluate it, you look at it like, look, 5s1, that's got an unpaired electron right here. It's going to be attracted to a magnetic field. Done deal, over, okay? If you have a species with all the electrons paired up, it exhibits what's called diamagnetism. That means it's not going to be attracted, and it's actually slightly repelled by a magnetic field. So if all the electron configuration, if all the sublevels are completely filled up, it's diamagnetic. So you need to be fully aware of these definitions. I can promise you that the ACS final always asks one question about, you know, is this paramagnetic? Is this diamagnetic? They love to ask that question. Anyhow, this is just a figure that comes from our book. If you take, and actually, I know that none of us are on campus a whole lot, but in my office on top of my refrigerator, I actually have a little demo of, you know, diamagnetic and paramagnetic ions. But what happens here is that if you have a sample that's diamagnetic, okay, and you put like a little bit of something that's diamagnetic, and like a little, it looks like it's in a balloon here, and then you put it near magnets, it's not going to be attracted to the magnet. However, if you have something that's paramagnetic and you turn an electromagnet on, it's going to attract it and it's going to pull the weight up. My demo that's on my fridge is not nearly that cool. Okay, I just basically took some paramagnetic and diamagnetic ions and put them in little pipettes, and then I have a magnet. You can push it away or you can pull it towards you. Anyhow, it's kind of a goofy thing, but I usually take it down to the classroom and face-to-face. So anyhow, not this semester. What else here? Write electron configuration and predict magnetic behavior of transition metals. Let's try the first one, cobalt 3+, and we'll see if it's paramagnetic. So cobalt 3+. First, let's start out by writing out the electron configuration of cobalt. It shouldn't take too long. Cobalt is element number 27 on the periodic table. I'll write it up top here. Cobalt is 1s2. You know what? Let's just draw this. Let's just do the condensed in the interest of time. So the noble gas that precedes cobalt is argon. So it's argon. What comes after argon? Then we have 4s2. So 4s2. Then we have 3d. Cobalt is 1, 2, 3, 4, 5, 6. Over. So we have, or sorry, is it 6 or 1, 2, 3, 4, 5, 6, 7. 3d7. Sorry, Mr. Dion needs a new prescription. Anyhow, when we form the cobalt 3+ ion, the cation, we need to lose 3 of those electrons. So we're still going to have argon. We're still going to have our core electrons. But which electrons are we removing here? Okay, that is the question. Well, the first thing we're going to do is we're going to remove electrons with the highest principal quantum number. So the first ones we're going to remove are the 4s electrons. Now, there's only 2 of those, so we need to remove 1 more electron, and that's going to come from the 3d orbital. So what you're going to be left over with is argon, is the core electrons, and then you're going to have 3d6 So if I read out the orbital diagram for that, okay, if I read out the 1, 2, 3, 4, 5, 3D orbitals, I have 1, 2, 3, 4, 5, 6. You can clearly see here that I have unpaired electrons. And so the cobalt 3 plus ion is going to be paramagnetic. That means it's attracted to a magnetic field. Let's try the mercury 2 plus. It's 1026. Yeah, we could do it quickly. Mercury 2 plus. So Hg 2 plus. The noble gas that precedes mercury, which is element number 80, is xenon. And so we'll put that in here. And so xenon, and then after xenon, we have 6s2, 4f, right? We have to dip down into the lanthanides, 4f, 14, 5d10, like that. And since we're only losing 2 electrons, we're going to remove the ones with the highest principal quantum number. And so what I first drew was Hg, and so now my Hg2 plus is argon, xenon, followed by 4f14 and 5d10, like that. Now if I read out all the 4f orbitals, 1, 2, 3, 4, 5, 6, 7. So there's 7 4f orbitals and 1, 2, 3, 4, 5 d orbitals. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's all full. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all full. And so this ion is diamagnetic. Okay, here we go. Or not paramagnetic is what I think it says in the solutions. Anyhow, there we go. Let's talk about the size of ions. And I officially think that this is the last thing that we cover, the last concept that we look at before your midterm, the midterm that's coming up on Friday. Okay. And I think that this concept is one of the more intuitive concepts that we look at in this class. And so, or sorry, in this chapter. And so it's kind of a nice, sweet way to end the chapter because students usually follow along with this pretty quickly. Is that it says here that cations are smaller than their parent atoms while anions are larger. Okay, ionic radius increases down a group, cation size decreases as charge increases. Okay, well, let's think about that. Okay, if I didn't mean to do that. Anyhow, the important thing is I'm not bitter. Okay, where was I? Here we go. Okay, the first statement: ionic radius increases down a group. Okay, as n increases. So what that means is if you went from lithium plus to sodium plus to potassium plus to rubidium plus, so on and so forth, since those are all in the same group, right? The radius of those ions as you go down the group, they're going to get bigger and bigger and bigger. Okay, cool. Now it says here that cation size decreases as charge increases. Now let me move this over here and I'll explain what I mean by that. So I'll move this up here. Okay, that's this concept right here. Okay, now cation size decreases as charge increases. See if you can follow me on this. Okay, so we have, let's just take potassium and calcium. So if we take potassium, K plus, and we take potassium, which is a 1 plus charge, and calcium, which has a 2 plus charge, okay? Think about it. Those both have the same number of what? Core electrons. It is both, those both have 18 core electrons. We could put that in here. Both have 18 core electrons. Okay, so they both have the same amount of shielding, but how many protons are in the nucleus of each one of these? Well, the potassium has 19 protons, so 19 protons, and the calcium has 20 protons. So that means the calcium has the same number of electrons, but it's got a greater positive charge in the nucleus. What's that mean? It's going to pull the electrons in even tighter. Give me a thumbs up if that makes sense to you. All right, cool, good. Okay, so it says here, an isoelectronic series. So an isoelectronic series is a series of ions that have the same electron configuration, but the ion size is going to decrease with increasing nuclear charge, right? So the higher nuclear charge we have, the smaller the ion will be, okay? Another way we can think about this is if we have an anion, that the electrons are going to repel each other. So let's take a look at what happens as we go across a period, or sorry, as we go across a group here that are all isoelectronic. So if you look at all of these ions that are in this box here, they are all isoelectronic one with another, okay? They all have the same number of electrons. So we could put here all have 10 electrons. Okay? Everything that's in this box, all the ions have 10 electrons. The sodium plus has 10 electrons. The magnesium 2 plus has 10 electrons. The aluminum 3 plus has 10 electrons. The nitrogen 3 minus has 10 electrons. The oxygen 2 minus has 10 electrons. The fluorine 1 minus has 10 electrons. So what's your point, Mr. Dion? Okay, I got it. They all have 10 electrons. Well, look at the relative size of the ions. The ions are shown in gray. As the ion gets more and more positive, right, as we go from +1 to +2 to +3, what are we doing? We're increasing the number of protons, but the number of electrons stays the same. So it's going to rein in those electrons tighter and tighter and tighter because the nucleus is getting bigger and bigger and bigger, more positive, but the number of electrons doesn't change. Okay, now let's look at the trend over here for nitrogen, oxygen, and fluorine. I'm going to go in this direction, okay? If we go from fluorine to oxygen to nitrogen, what are we doing? We're adding more and more electrons, but that nuclear charge stays the exact same. Okay, sorry, the nuclear charge is staying. Sorry, the nuclear charge is changing, but the number of electrons is. Sorry, I'm getting tired. Okay, the number of electrons is increasing. Okay, and the nuclear charge is decreasing. So what does that mean? That the electrons are going to be held less and less tightly. Another way that you can think about it is that the more negative charges that you have, is that those outer electrons are going to repel each other. Okay, they're going to repel each other slightly, and so the atomic or the ionic radius is going to get larger and larger. Does that make sense to you guys? Give me a thumbs up if you follow me on that. The higher the charge on a cation, the smaller the ion is going to be, and the higher the charge on an anion, the bigger it's going to be. Sorry, I'm just getting really tired here. Anyhow, there we go. I have organic chemistry before this, and this morning it was a tough lecture for them, so I'm tired of screaming. I was screaming for 75 minutes before I even get started here. All right, well, with that in mind, look, I can promise you, there's 3 absolutes in life: death, taxes, and the ACS's final loves to ask this question, okay? They always throw this chestnut in there where they give you a bunch of ions and they just say, rank them in order of size. So let's give the first one a try. And I think that this will officially be the last problem that we'll look at in this chapter. And the last problem we'll look at before midterm country. By the way, if you showed up late to lecture, if you go back in the chat, way back to the beginning of the class, I posted links to the videos that go over the entire practice midterm from soup to nuts, okay? Covers every single question in the practice midterm. So if you want to try the practice midterm right after class, and then maybe take a look at the video to make sure that you fill in all your, maybe if you have any weak spots, then I would recommend doing that. Okay, well, with that in mind, let's take a look at an example, and I'm going to skip right ahead to the toughest one. Let's go right here. Come on, let's do it. We can do it. We have gold with a 1+ charge, and we have gold with a 3+ charge. Which one of these do you think would be bigger? Okay, so we'll put here larger, largest, smallest. Not a trick question. Which one would be the largest? Yeah, okay. All my students are saying the one with a 1+ charge is going to be bigger. Why? Right? Why is gold with a 1+ charge bigger than gold with a 3+ charge? Let's evaluate it. Okay, gold is element number 79 in the periodic table. That means it's got 79 protons in the nucleus. This guy's got 79 protons. This guy's got 79 protons. How many electrons are there in gold 1 plus? There are 78 electrons here, and there are 76 electrons here. Now, if I have 79 protons, right, and they've got 78 electrons to rein in, they're going to be able to pull them in. But if I've got less electrons and the same number of protons, it's going to be able to pull it in a little tighter and make it a little bit smaller. Throwing down my Apple Pencil. Does that make sense? Give me a thumbs up if you follow me on that, because if you do, boy, you are in good shape, my friend. Okay? Good. That's great. This is kind of a fun concept to end the chapter on. Let's go backwards. Let's try the next one. You have potassium with a 1 plus charge, sulfur with a 2 minus charge, and chlorine with a 1 minus charge. I'm going to help you out with this one. All three of these ions, look at this. Can you believe it? I'm getting excited, okay? They're isoelectronic. Can somebody tell me what element, not what ion, what element they are all isoelectronic with? Not a trick question. They all have the same number of electrons as who? Argon, right? They all have 18 electrons. So we can put here all isoelectronic with argon. So what's going to be the biggest one? The one with the most negative charge, right? Those electrons are going to be repelling each other. Quit crowding me, bro. You know, get out of my space, okay? So you're going to have the sulfur 2 minus is going to be the biggest. Then you have chlorine is still negative. And then, oh man, the smallest one is, of course, the one with the positive charge. You got potassium, it's got 19 protons, but you got the same number of electrons, right, in a positive charge. So potassium has the most protons for all of these. Okay, so potassium is going to be the smallest, the potassium ion. All right, 1038, we got one more. What do these last three, what do these three all have in common? Calcium 2 plus, strontium 2 plus, and magnesium 2 plus. They all have something in common. I bet you can identify what that is. Yeah, thanks, Violet. They're all from the same group, right? They're all in group 2A. Okay, and what was the rule? As the principal quantum number increases, size is going to increase. So which one of these has the highest principal quantum number? It's strontium, which is in period 5. And so we'll put the strontium cation here. Which one of these is going to be the smallest? It would be the magnesium, which is in period 3. Okay, the magnesium cation. And then the calcium cation is in period 4. And there you have it, my friends. It's 1039, and we covered every little bit of content that you need to know to do that practice final. Okay?